Hi, welcome back to Kine 3030 Online. Today we're going to tackle a really important area of biomechanics of human movement, and that is torque. Because as we've talked about, muscles create torque. Strength is torque. So much of what we do is rotational motion around joints. And since it's rotational, we're talking torque. Muscles have to create a torque. So this is just a quick review of what we did last class. And last class, of course, we did friction and ground reaction force. And you see in here, you have the free body diagram of a person jumping. There is their force due to gravity down. And there's the two components of the ground reaction force going up. So there's a few questions here about what would be happening here. If the person went straight up, if their center of gravity went straight up, would there be a horizontal or frictional component of the ground reaction force? Let's think about it. Force equals mass times acceleration. So if we have an acceleration in the horizontal direction, then we need to have a force in the horizontal direction. If we have no acceleration in the horizontal direction, if we go straight up and straight down, there was no force there's no acceleration in the horizontal direction, which means at that point there was no frictional component of the ground reaction force. It was a pure push so that we would go straight up. That doesn't mean that you don't have to recognize the potential for that component, because it could be there and it just might equal zero, as I said, if you went straight up. If they jump forward, which direction would it be acting? The frictional force would be acting forward on the shoe, okay? Backwards on the ground, forward on the shoe. Even though I said that it was opposite movement, and remember, that was the movement of the ground with respect to the shoe, not the movement of the person. So the ground reaction force frictional component on the person, on that free body diagram, has to point in the direction they're going to accelerate, which would be forward if they're jumping forward. And ideally, that's of course going to be static, because if you're jumping forward, you don't want your foot to slip backwards. If your foot slips backwards, you're just not going to develop the same amount of forward acceleration that you would like. In order to take off, that ground reaction force push component, so the pushing straight up part, has to be greater than weight. So think about that from Newton's second law. Sum of the forces equals mass times the acceleration. If I want to accelerate upwards, and I can only accelerate upwards until my feet are off the ground, because then I become a projectile. So if I want to accelerate upwards, that force underneath my foot has to be greater than the force due to gravity down. Does that mean the frictional force is greater too? Well, that's an interesting question, because that means the potential for the frictional force is greater. Because, of course, friction equals the coefficient of friction times the normal force. And so the greater the normal force, which would be greater the push component of the ground reaction force, the greater the potential for friction would be. Might not all be used, but a greater potential is there. So today we're going into, as I said, into torque, which is that hugely important idea in a body which is made up of a whole bunch of rotating joints. And we're going to look at factors that affect torque and think of levers. We're going to think of the whole musculoskeletal system, a joint, a muscle, and a bone, as a lever, and we'll review levers. And look at how we might actually state some of those questions. So, a person is sitting, doing knee extension exercises, and you observe that the lower leg rotates at the knee. That seems logical. And you know muscles pull. How can a force that pulls cause rotation? So we come back to torque. We have defined it before, but I'll just review that. And it's the rotational effect caused by an applied force, by a linear force. Also called moment of force. Sometimes by instinct, because often in the research literature it is a capital M as opposed to capital T, but still. So if I apply a linear force as I come to a gate, and it's held at the one corner by the pin joint there, if I push on that force, the gate is going to rotate around that axis of rotation that occurs at the hinge. If there wasn't a hinge there, me pushing on that gate would just have the whole gate moving forward, but it rotates. And the amount of rotation, that torque, equals the force that I'm applying times what's called the moment arm. And the moment arm is this distance, and it's if you took the line of action of that force and the axis of rotation, and you drew a perpendicular line, meaning it's 90 degrees to that direction of the force, back to the axis of rotation, that distance is my moment arm. You can also have something called a pure torque, where something just literally creates the torque. It isn't because of an applied force going here, but there is something that just creates a pure torque, like a torque engine. You can see the importance of moment arm in this if you've ever used a wrench. If you take the exact same force and you apply it in two places in the wrench, and your axis of rotation, of course, is where your wrench is holding onto the bolt, I am going to create a much bigger torque by exerting that exact same force farther away from the bolt. So in something like putting on your tires, in the spring, your summer tires, and you're undoing the nuts, you want a kind of a longer wrench, because that way, you'll have more force to unscrew it, and then you'll be able to create, more torque. Same force. For the same force, you'll create more torque for undoing the nuts, and then you will create more torque, very important, to tighten those nuts back up. So the farther you are away from that axis of rotation, which is where the wrench grabs hold of the bolt or the nut, and you're going to get a greater torque. As I said, the moment arm is the perpendicular distance, 90 degrees from the line of action of the force to the axis of rotation. This becomes really important in how our muscles attach to the ground, or to the bones themselves. But in the situation shown here, in all cases here, the applied force is perpendicular to the gate itself. So it's pretty easy there to go from where the hinge is on the gate to where the force is applied, because the force is 90 degrees to the actual gate. But that isn't always the case. So if we looked at, that would be the top situation here. If we looked at a situation like the middle one, where the force is sort of aiming inwards at the same time, you can see you have to follow that whole line of action of the force until you get to the point where if you drew a line from that line of action at 90 degrees to it, it would pass through the axis of rotation, the hinge, and that would be your moment arm. Similarly, if you're going out, pushing out on it, instead of straight on, but pushing a bit out, you would have to go back on your line of action, extend your line of action, so that you could draw a line that was 90 degrees from that line of action to come back to your hinge, or axis of rotation. To increase torque, you therefore can either increase your force or you can increase your moment arm. So you can pull harder on something, or you can move your hand farther away from the nut in the case of a wrench, because you are increasing the moment arm. Either one will increase your torque. Like forces, torques are vectors. The only difference here is that we typically call it clockwise or counterclockwise. Often in biomechanics, counterclockwise is considered positive. If you're just doing clockwise, counterclockwise. On the other hand, a lot of the times we are doing rotation around a joint, and we all know that rotations around the joints are things like flexion extension. Then we can put them into an anatomical framework like flexion extension, abduction, adduction. And in those cases, there is no set, this is positive and this is negative. You draw your free body diagram, or you put in your graph what you consider positive and what you consider negative in that situation. So, in a mechanical framework, clockwise, counterclockwise. But let's just think about how this really applies to movement. And we're going to try and go back to levers. What's a lever? Lever is a simple machine. You learned it way back in elementary school, and it's basically a rigid bar and an axis of rotation called a fulcrum, and then a load force, something that you're trying to move, apply force to, and the actual applied force, how much you actually have to put on it. So we have the applied force, the resistance force or load, and the fulcrum and the bar. And how you rearrange your fulcrum and your two forces on that bar makes a difference on what kind of advantages you're going to get. And they fall under different types of levers. So, 3 different types. The first type, or first class lever, is your basic teeter-totter. And you have the axis of rotation, the fulcrum. The axis of rotation is in the middle, and your load force or resistance on one side and your applied force is on the other side. It has numerous advantages depending on where that fulcrum is with respect to either the applied force or to the load force. You can have advantages of balance, hence a teeter-totter. It can be advantageous of range of motion, or it can be advantageous in force, meaning one person does not have to exert as much force as the other person. If your force is your weight, you can imagine you could have, by taking somebody who's much lighter, say a parent with a child, and the child goes all the way out and sits at the seat, whereas the parent has to be close to the fulcrum in order to balance out the child, because it's torque, it's not weight. Second class is where you have the axis or fulcrum at one end. You have your load in the middle, and you have your applied force at the end. And the last one is the third class lever, where again your fulcrum or axis of rotation is at one end. The applied force is in the middle, and the load force is at the end. So in the second class lever, you have great advantages in terms of force. You do not have to exert as much force as you are going to be applying onto the load. Whereas in the third class lever, it's the opposite. You do not have no advantages in terms of force, but what you do have advantages of is speed and range of motion. So think of here, if this is a force that's being applied here, and here's my my load here in my hand, and here, it's my muscle here. You can imagine that for doing here, I don't have to change the length of my muscle as much as I get that full range of motion of my hand itself. So you can see that by being in a third class lever, which a lot of human joints are, not all, but most for movement, means that we can get a lot of movement at the end of the segment from a small amount change in length close to the actual joint itself. Recognizing that there are no advantages of force, meaning we actually have to create more force in our muscles than we are than the load we are going to support. So a mechanical advantage does capture that whole idea of the force advantage. And you take the moment arm associated with the load, that's called the resistance arm, and we take the moment arm associated with the applied force, and that's called the force arm, and you look at the ratio between the two, and that's the mechanical advantage. If the mechanical advantage is less than 1, which you get in a first, you can get in a first, and you do get in with a third, it means that the applied force has to be greater than the resistance force. So the applied force is going to be greater than the actual load. It does mean we have great advantages on that range of motion, as I discussed, but not on force. Whereas if it's greater than 1, which happens always in a second and sometimes in a first, it means you don't have to generate as much force as the load that you are trying to move. So you would choose something for like that first class, and there's some examples in your book of different levers, but that classic one of using a pry bar to move, let's say, a big heavy rock, and you make the moment arm associated with rock small, and the moment arm associated with you pushing on the pry bar large, that's going to have a mechanical advantage greater than 1, and it means that you can move a heavier rock than you are able to generate the force for. As I said, most of the levers in the human body are third class, and that promotes speed and range of motion, but muscles must exert, in most cases, greater forces than the load that they are trying to overcome. So, if we come back to torque in the human movement, we have, again, human movement depends on rotation of body segments around joints. Rotations are caused by torques Therefore, human motion is caused by torques created at each joint. And muscles create a torque at each joint because their line of action is offset from the joint center. Our muscles do not cross through the joint center. The joint center is bone. Our muscles are offset from that joint center so that they have a moment arm as they cross. And the amount and the direction of that moment arm is what establishes which direction they're going to rotate around the joint and how much muscle force you need in order to rotate around that joint. So that's you need to have that moment arm, and it's that moment arm that's going to give you the torque. So if you think of our joint as a lever, and again, the center of the joint is the axis of rotation. Kind of think of it as a fulcrum. And the muscles pull. They don't push, they can pull along a line defined from the origin to insertion. And because that is offset, they're going to create a torque around the joint. So it acts like a lever. In this case, you can see the applied force is the muscle. The fulcrum is the joint center, the axis of rotation. So axis of rotation and fulcrum, same thing. And the load in this case is actually twofold. It's the weight of the forearm and hand, and it's the weight of whatever load they have in their hand. How does that look in a free body diagram? Exactly what is shown there. We have the forearm and hand. That's one horizontal stick in this particular case. We have at the fulcrum itself, and I talked about this is a pin joint free to move. You have the two forces at the pin joint, at the joint itself, which just hold that joint in place. Kind of represents the bone-on-bone force. And in the elbow itself, we have the applied force, which is the force of the muscle, and we have the two load forces, the weight due to gravity of the forearm and hand, and then another weight due to the weight that's in the hand itself. And of course, there was a reference frame, so you knew which way was positive when you were doing your equations of motion later. So again, you can see where the four parts of that lever come into being. You have the bar, you have the fulcrum, and here are just some examples of that in action. And in each case, these are just using the weight of this. The load is, in most of these cases, the actual weight of the body segment itself. So in the case of the one on the left, that you've got your fulcrum at the elbow, you've got the applied force of the biceps, and you have the load of the weight of the forearm and hand. Similarly, in the second one, you have, again, your fulcrum, which is your center of rotation in your knee, your applied force, which is the force being created in the patellar tendon from the quadriceps, and the weight of the calf and foot. And in the last case, you can see the fulcrum, which is the center of rotation of the glenohumeral joint, and you have the muscle pulling, medial deltoid, and you have the weight of the upper arm. So you need to know a moment arm. Well, you have a distance of attachment, L. You have an angle of attachment, and we've talked about what the angle of attachment is. That's the angle between the muscle and the bone itself on the side of the joint. That's the angle of attachment, and the distance of attachment is from that joint center to where the muscle attaches. And you can now find a triangle there because your moment arm is going to be perpendicular to the line of action, of this case your biceps. And so you're going to draw a line that goes perpendicular from that biceps and then passes through the axis of rotation. And that is the moment arm of the muscle. If you do the math for that, the distance of attachment actually becomes your hypotenuse, and your angle of attachment becomes the is the opposite. And so you have distance of attachment times sine theta, sine angle of attachment, is going to give you the moment arm of the muscle in that case. Now, let's skip back a few lectures, because in those a few lectures ago, I talked about muscle creating these rotary components and stabilizing components, and you can multiply the rotary component by that distance of attachment in order to get the actual torque created by the muscle. You know what? Those are actually saying the same thing in just different ways. If you look at the rotary component, which is that component that is 90 degrees to the bone, and that's going to cause pure torque. So you're taking your muscle and you're splitting it into parts that are perpendicular to the muscle and that are along the axis of the muscle. And the stabilizing or dislocating components are, again, along the axis of the, axis of the bone, axis of the bone. And they either pull it into the joint, stabilizing, or pull it away from the joint, dislocating. So a torque is created by a force times a moment arm. And if you took the stabilizing component, if you took the rotary component and multiplied it by the distance of attachment, that would be a pure torque. That would be the portion of the muscle force that is causing rotation. If you took the stabilizing component and multiplied by its moment arm, it has no moment arm. It acts directly towards the joint center, so it actually has no moment arm. So the stabilizing or dislocating components actually play no role in terms of creating torque. So now I've shown you two sort of ways of expressing the torque created by the muscle. The first one is take the muscle force and split it into two components, one that's perpendicular to the bone and one that's along the axis of the bone, and multiply that one that's perpendicular to the bone by that distance of attachment. And the other is to take the, figure out what the actual moment arm of the muscle is by taking the angle of attachment and the distance of attachment, and considering that the hypotenuse and the opposite components of a triangle, so that you can actually calculate your moment arm, and multiplying that by the actual force in the muscle. If you do the math, sit down and do it so that you can see both ways, you come to the same thing. In one case, you're multiplying the sine theta of it, so sine times the angle of attachment to the force before multiplying it by the distance of attachment. In the other one, you're multiplying the sine of the angle of attachment to the distance of attachment first before multiplying it by the force. So it's the same thing, they just different directions of doing your math. So if we come back to our original problem, which is how can a force that can pull cause rotation? And a muscle creates, again, force and pulls off axis. That's the applied force. And the weight of the lower leg and attached weight are the resistance. And therefore and your knee joint, of course, is your fulcrum. And you are therefore going to create a torque, and torques in two directions. In this particular case, does the quadriceps develop much rotary force? No. In that particular direction, the posture, hopefully you can see that the generation of the force doesn't have the best moment arm that it could have, but as you go through the range of motion, that it improves. But on the other hand, in this particular case, the load doesn't create much of a torque either, so it's a situation which balances each other out. So we have talked about torque and how you define it and how you calculate it, and looked at torque in the levers, or how important torque is in levers, and how those levers can affect the amount of applied force for the load that it has to overcome, and how in particular in many joints muscles act as a third-class lever in a system with a bone, a joint, and a load at the end of the segment.